I assume that the audience here are know something about Lie groups. So let me just very briefly recall some notation. A Lie group is also a C-infinity manifold with a group structure. G with a group structure. By this I mean it has a product has an inverse map which maps each element to its inverse and has a unit. A distinguished point, so that this system satisfies the usual group axioms. Yeah, this is actually we even just from the linear algebra you can find many examples of Lie groups. Maybe the simplest one is the circle group in the complex plane. You let theta vary in reals. So it draws a circle in the complex plane. So this is S1. And you have also the torus group, which is a Cartesian product of n circle group. But this they are manifold and also has canonical product and inverse and unit. But this considered as a Lie group, they are all abelian. I mean, the product is actually commutes. But for more general case, let me set F to be the reals or complex or the algebra of quaternions. In this case, let me put F to be the set of square matrix of rank n with ij tag value in the fixed F. This is a vector space, can be considered as a real vector space. With dimension n square or 2n square or 4n square, depending on F is real or complex or quaternions. You can easily calculate this, the dimension as a real vector space. And inside this vector space or Euclidean space, one has a subset which consists of those matrices satisfy the constraint that each matrix you can do the conjugation, which denoted by tau, just reflection along the diagonal. You have also this is the transpose, and also you have conjugation, which you put -1 at the imaginary part. So this gives you a subset in this matrix space. Actually, in this space you have operation like product, which simply maps two matrices to their product. You also have a map which maps each matrix to the transposed conjugation. And you also have the identity matrix. This is not group, but if you restrict this operation to the subspace, this becomes a Lie group. You can simply verify if you restrict this IB to be this set, then the value is again an element here. Also, if you take I inside here, then you do this operation, it is again an element here. So with this structure, this automatically becomes a Lie group. This is a Lie group. These Lie groups are called the classical Lie groups. More precisely, if we take F to be reals, then you get the orthogonal group of order n. And if you take F to be the complex numbers, then you get the unitary group of order n. And finally, in the case of quaternions, you get so-called symplectic group of rank n. And all this family gives you the so-called the classical groups. And apart from the classical groups, there are also 5 exceptional Lie groups. And there is a general theory by Gardin which says that almost locally, every Lie group G is a product of this and this guy with several exceptional Lie groups. So these are some kind of very basic examples of Lie groups. Now, in the second part, I will talk about something about called stiff diagram of a Lie group. So let me, in each Lie group, you can find a maximum subgroup. So let me see. Abelian. Subgroup T of G. You can always try to find a maximum subgroup of this Lie group G, which is abelian. And this group is called the maximum torus of G.
You're assuming that through this label is compact?
Yeah, compact. Yeah, we just talk about a compact Lie group, which is called maximum torus of G. Why I give the name of torus? Because this kind of group must be of this form, which is a Cartesian product of several circle group. So the dimension of this T is the same as the number of factors of S1 involved So the dimension of T is called the rank of G. And in this very special case that G is one of the classical groups, you can easily find the maximum torus, just the diagonal matrix inside this group. In each group you have diagonal matrix. They are abelian. Diagonal matrices are all abelian because the product all commutes. So in these cases you can easily find this this maximum subgroup. What we so let me explain what is a Stifel diagram of a Lie group. The exponential map induces a diagram where LG is a tangent space to G at the unit. So suppose we have a Lie group G here with unit E, then here you have the tangent space at this point. This is in Lie group series, these are sometimes also called the Lie algebra of G. But we don't need this Lie algebra structure. We need the structure of this as a real vector space. We will consider this as a real vector space. The exponential map is simply maps each line pass through this origin of this vector space to the Unicode geodesics down below. So this map is also considered as a exponential map of arbitrary smooth manifold. You can always get this this exponential map. Also, similarly, this L of T denotes the tangent space to T as the identity. This is naturally a subspace in this vector space, and because T is a subgroup inside this G, so this you have this diagram. And also in this series, this is called the Gardin subalgebra. Using this picture, we can define in this set. You see, in Lie group theory, people always want to understand the geometry of this guy. But a very good thing is that you can always lift the geometry of this manifold into something in this vector space. So this is a very simple one because this has a dimension very small, and which is given by the exponential map of the torus. So this is the simplest one. This one is simple. This could be considered as complicated. I think the beautiful part of the Lie group theory is you can try to understand what happens to the geometry of G by doing some vector calculus in this vector space, which has a dimension very small normally. This was so. Let me introduce some very crucial notation here. So let me call a vector is called singular or regular. If the centralizer of A has PU I need to explain this. So suppose we give a point inside G, the so-called the centralizer of G at X. Is those elements in the Lie group which communes with X on the group multiplication. So I will call a vector here a singular. If I use the exponential map, send it to G, I compute the dimension of the centralizer. If it really bigger than the dimension of T, I call this singular. Otherwise, it called regular. The centralizer always contain. This is the normal property that the centralizer is always containing the maximum torus. If it really equal to the maximum torus, we call this point regular. Otherwise, which is called singular. So in what follows, I use D of G to denote the set of vectors which is singular. The interesting part of this notations is that this set has very good geometric property. I use the next theorem to describe it. I have explained what is the rank of a Lie group, which is simply the dimension of the maximum torus. And I will set M equal to half of the dimension of G minus the rank of G. Yeah, this is always an integer in every case. Then the first conclusion is that they are precisely M hyperplanes. Says L1 in the Gaussian subalgebra such that D of G are the union of these hyperplanes. So this is although from the definition it may think that the singular this set could be very complicated, but actually not. They are consist of hyperplane. I should say through the origin. The origin in this vector space. Second property is that if we let L chi be the normal line of the hyperplane L chi through 0, then the exponential map maps L chi to a circle subgroup of G. Here inside this vector space Lt, we have a hyperplane through 0, which is called L chi. Suppose we take a case 1. Then there is a unique normal line, which is perpendicular to this hyperplane through 0. Then this second property says that if you apply this exponential map, like this is a line inside here. If you apply this exponential map to this line, what you get is a circle inside G. Normally, if you apply exponential to a line to this, which may not be a circle subgroup, which cannot be normally not closed. But exactly if you take this normal line down to the group G, you get a circle subgroup of this G. And the third property is very crucial to why the idea of both Simonson resolution appears. If we let Kr to be the centralizer of exp applied to the R's hyperplane, then the maximum torus is always a subgroup of Kr, and the quotient of Kr is a two-sphere. Yeah, I'll explain this by drawing picture. I will be unable to draw picture for higher dimension, but I can draw picture for SU3 and G2, the first exceptional Lie group. In these two cases, maximum torus are all rank 2. So this is a vector space, just a dimension 2, so I can draw the picture. This is LT. This is also LT. And in these two cases, if we want to find these hyperplanes, in the first case, there are 3 hyperplanes. So-called singular plane. And in the third case, there are 6 hyperplanes. Let me say L1, L2. I need to explain this notion, this notation. So if you apply this exponential map to a plane, then you get a subset in this group G. Then the element in G which commutes with everything in this set is called the centralizer of this subset. This is defined similar to the centralizer of a point. Yeah, this result is very basic because just from this picture, you can get everything you want to describe the geometry of Lie group. Let me just explain in the next part of this. Yeah, this picture is called the Stifel diagram of G.
Theorem is due to balance and
yeah, let me see. This is a way I try to understand the Lie group. Then we'll see. Then I summarize these 3 properties, and from these 3 properties, we can get everything about the Lie group. This is a way I try to understand the Lie group theory. So just from this theorem, we can get everything from about Lie group. The first notion is concerned with so-called Weyl chamber. So these planes, or these hyperplanes, in dg divide this vector space into finite many convex cones. Just as the picture show you, you can divide this space, this hyperplane, cut the space into convex cones. And each one is called a well chamber of G. It is more convenient if we fix a regular point. A point is regular if only if which is not on this hyperplane by the definition. So fix a regular point says x naught. The well chamber containing this point is called fundamental well chamber. Of G. So if you fix one, there is precisely one well chamber containing this point. So this is called so-called fundamental well chamber. Yeah, the next notation will make use of the second property. Let plus or minus r chi are two vectors on this normal line. Non-zero vector such that under exponential map they will map to the identity. Just because the exponential map maps this line to a circle, suppose this is 0. If you start from 0, turn around here, then correspondingly, there are two vectors. If we denote one by alpha chi, another must be minus alpha chi, with minimal length, so that which maps on the x to the unit. And with these two vectors, is called the root system. So the root system of a Lie group G, just these normal vectors of this hyperplane, which maps to the identity by the exponential map. Also, the integer. The number. Two times the inner product module this the length of the first vector. Actually, this can only take the value 0 plus or minus 1 plus or minus 2 is called the Gardner integer. Of this alpha I and alpha j. This property, I think is also somehow a miracle come from the Lie theory. Whenever the two vectors you take from this set, you can always only get only 0 plus or minus 1, 2, 3. No other integer will appear.
To alpha I, alpha j in a product.
In the product,
Divided by
the alpha I, alpha I.
Alpha I, alpha I.
Yeah. Yeah, normally the root system consists of too many vectors. Actually, this has 2 times n, 2 times m vectors. There are too many. But if you look at one well chamber, you can eliminate this to get something even more basic than this one. So let me assume that in the set of M hyperplane, the first n are exactly the boundary of this fundamental well cell. So I can always make this assumption. Assume that the first n hyperplane in the Stiefel diagram are the walls or boundaries a fundamental chamber. There's a set of vectors R5. Is called a system of simple roots. So you just fix a one well chamber and to look at the boundary hyperplane. Then you take one vector which perpendicular to the boundaries and point inwards this, then you get so-called a system of simple roots of T, which is normally much lesser than this set. This set could consist of many vectors. is called the Gardner matrix. Actually, there is the Gardner matrix has a property that two Lie groups are locally isomorphic. Locally isomorphic means that differs by a covering, which called locally, if and only if the Gardner matrix of G equal to the Gardner matrix of G prime. So actually, up to local isomorphism, this Gardner matrix classifies these Lie groups.
You're taking simple roots. You have two directions of this vector.
Yeah.
So you're taking
the one point inverse. Inverse one. So another notation is also very important. Again, for a singular plane. Belong to this dg. Let sigma chi belong to the automorphism of this Hall vector space. Reflection in the hyperplane. You have a hyperplane, then it defines uniquely a reflection along this hyperplane, which belongs to the automorphism group of this. Then the subgroup generated by these reflections is called the well group of G. Yeah, from the definition, it seems that this well group has many generators, one-to-one corresponding to these hyperplanes. But actually, there is a well-known fact. If you fix a well chamber, you look at the reflection along this wall, then W has a set of generators. So this element sufficient to generate. It's a minimal system of generators for this W. So it seems that we have involved many notations up here, because all this will appear in Bart Simonson's work. But there is a very easy way to remember all this. You just keep in mind this result. You see, this theorem is very easy to understand. So once you acknowledge this fact, you can easily find out the subsequent notation by yourself. Because for each, these planes must divide this vector space into many convex halls. So each one is called Weyl chamber. So it's very natural. And also, each hyperplane also defines a reflection. So these reflections must generate a subgroup of the automorphism group of this vector space. So this is called Weyl group. And because of this property, you can easily find two vectors, two normal vectors, which maps into the unit. So you take off all these vectors, you get so-called the root system of this D group. And if you only take off the normal vectors to the boundary of this Weyl cell, then you get so-called a system of simple root. This is some kind of the set of all root. These are simple roots. And also, each pair of root gives you a number. Actually, this number records the geometric shape of this Weyl chamber. This
number what does this geometrically mean?
This means somehow the angle, you see the inner product detects the angle of this complete rule, but you only divide, but you need to divide this number by the length of this, the first vector. This records the geometric shape because these are very simple, but in dimension 3 you could have the Weyl cell could look like this. Then these are boundary planes. Actually, this matrix describes the geometric shape. What I mean is the angles between different hyperplanes together with the length and take into also the length of these vectors because this tells you along the normal line toward length you really get a circle back in the Lie group. So actually the Gardner matrix is very fundamental for the Lie group theory. So all this notion will appear. What I could say that this integer will appear as in next talk will appear as the structure matrix of the Bart cycle. Bart will appear at that place, and this result will make of you this result, which will involve to tell you why this Bart-Simpson cycle is really a Bart manifold. This property, but I will make use of this third property next time.
But in this case, these Bij's are all only plus minus 1, 0, 1, 2, 3.
Yeah.
Right?
Yeah.
So
you're right. Yeah. So the Bart manifold are special, very special. The structure matrix only involve this this kind of number. Yeah. Also, the value group is also important because we shall say that this manifold, the Schubert varieties inside this manifold are one-to-one corresponds to the Schubert variety. See here. Normally denoted by XW, which is a subvariety in this manifold, but the W is an element in the value. So we will see that this W is actually the parameter for this so-called Schubert variety inside G over T. And also this picture are very important. Next time I will make use of this picture. I think the board Sampsons I can do something here just because they're familiar with this picture. You see, actually this value group can also geometricalized at here, because if you take a point here, you let this Wx at this point, then you get the orbit of this original point. In each value cell, there is only one orbit, one point.
Orbit by the value group.
Yeah, value group. So every value group element is determined by its orbit along this. So you can find this W as a point in the orbit of it.
So that's the number of the value chamber.
Yeah, it's the same. Yeah, the same thing. So next time I will start with this picture. Yeah. Thanks.